Hello guys, welcome back to a new session. We are in section 2 of chapter 9, which is about the organic compounds. In this section, we'll be talking about some of the unique properties of carbon and what are the organic compounds. We will define the organic compounds. Guys, the organic compounds are those compounds that mostly they contain carbon as the main element, but it's not true to say always the compounds that they contain carbon are organic. So let us discuss what are the compounds which are the organics. What are the compounds which are the organics? All organic compounds contain carbon, but however, not all carbon containing compounds are classified as organic, guys. For example, we have got sodium carbonates, carbon monoxide, carbon dioxide that are considered as inorganic. So we can say all carbon containing compounds except the carbonates and oxides are organics. All organic compounds are covalently bonded carbons containing compounds, excluding carbonates and oxides, excluding the carbonates and the oxides. Carbon oxide, whether it's monoxide, dioxide, trioxide, or any metal with the carbonates, sodium carbonate, potassium carbonate, magnesium carbonate, and so on, guys. But we can say usually those of the compounds that we deal with, if they contain carbon and hydrogen together, are what are classified as organic. Examples for the organic: C2H6, C3H8, C6H12, or 6, they are all organic. We will be naming the structures later and we will learn how to name those structures, guys. Carbon, it has many unique properties. One of the properties is that it has tendency to bond with the other atoms in a chain or a ring form, other atoms of carbon, and it has tendency to bond with the other elements, which are usually the nonmetals. So the diversity of organic compounds result from the uniqueness and special of carbon's structure and bonding. It has a tendency to bind to itself and to bind to other elements, to bind itself in different arrangements. We'll be talking in different arrangement, we mean in the form of the chain and the form of the ring. Let us talk about how it can bond with itself, guys. Carbon-carbon bonding. In chemistry, whenever an element has tendency to bond with this itself in a chain or a ring, we call as the catenation. So this type of bonding we call as the catenation. The covalent bonding of an element to itself to form chains or ring. To form chains or ring. The carbon has tendency to form bond with itself. Have a look on this, guys. Carbon bonded with the other carbon. So this is the catenation bonding. It has tendency to bond in single, double, and triple bond with itself as well. And the tendency of bonding with itself provides us two structures or two shapes, whether in the form of a chain or in the form of a ring. As you can see, here we have got chains and rings, thus ring-shaped structures. The carbon bonding to other elements, guys. Carbon, as it has tendency to bond with itself, it has tendency as well to bond to the other elements. The best example for this is the hydrocarbons. And we'll be talking about the hydrocarbons in section 3 and section 4 in detail, all about the hydrocarbons. Hydrocarbon is any compound that contains hydrogen and carbon. Like, well, for example, here we have got C2H6, C3H8, ethane, and propane. There are two hydrocarbons. There should be more than these hydrocarbons, and we have thousands of hydrocarbons. In hydrocarbon, guys, the hydrogen bonded. Let me draw the bonding structure of C2H6. Here we have got C2H6 structure. As you can see, the hydrogen bonded with the carbon, that's the carbon bonding to the other element. Carbon usually has tendency to bond with the elements which they do have the similar electronegativity. So usually the nonmetals, it has tendency to bond with the similar electronegativities elements, like the nonmetals of oxygen, nitrogen, sulfur would be halogens and hydrogen. So 8 elements: the fluorine, chlorine, bromine, iodine, oxygen, hydrogen, sulfur, and nitrogen are those nonmetals. Usually the carbon has tendency to bond with them. Example: C2H5OH, C6H5NH2, CH3COOH. They are all carbon containing compounds and carbon bonded with the other elements. Here we have got a strawberry with the cream over it. As you can see, the carbon in the structure, these carbons and the hydrogen are bonded to the carbons in the structure, guys. The arrangement of atoms in carbon, guys. The carbon, another unique property of carbon is that the same molecular compound of carbon has a property to show different structures or different arrangement of bonding, and this we call as the isomer we will be defining. The bonding capability of carbon allows for different arrangement of atoms or different structures in the bonding geometry. Some compounds may contain the same atoms but have different properties because the atoms are arranged differently. For example, guys, a simple example, the molecular formula for C2H6O can be shown in this structure and the other structure as well. As you can notice, how many carbons do we have here? C2. And hydrogens are 6 and 1 oxygen. Here the same, 2 carbon, 6 hydrogens and 1 oxygen. But in this, when the oxygen is in the center and bonded with the 2 hydrocarbons, we will talk about this, we call as the ether, guys. And these are the methyl, so the alkyl group connected to the oxygen we call as the ether. Dimethyl ether, this is the name of this structure, and the structure is changing. But as we have the hydroxyl group in the structure OH, it becomes alcohol, it becomes ethanol. Ethanol and dimethyl ether, they have got the same molecular formula, but different structure and different naming and different properties as well. This in chemistry we call as the isomer. Isomer is what? Have the same molecular formula but different structure, as we have represented, having the same molecular formula but different structure and different arrangement, different naming and different properties as well. We have got 2 types of isomer, guys: geometric and structural isomer. We prefer to talk about the geometric and structural isomer at the end of the chapter, at the end of section 4, because first we have to learn the section 3 and section 4. We have to learn the naming, the nomenclature of the alkanes, alkene and alkyne with the benzene, and then we'll be able to understand the naming and the geometric of the isomers. The representation of a chain hydrocarbon, we have got a formula we call as a structural formula. In structural formula, three information should be provided. First, the number of the atoms in terms of how many carbons, how many hydrogen, how many oxygen, how many sulfur are existing. Second, the type of the atoms. So the number of the atoms must be represented. Second, the type of the atoms must be represented. What are the types? Are they all hydrocarbons, hydrogen with carbon, or there should be some other types? And the arrangement of atoms, the geometry, the arrangement, the structure of the atoms should be represented. For example, here we have got a full molecular formula. How to represent, how to draw a structural formula for that molecular formula? Always, guys, always, the number of the carbons connected, write the number of the carbons with each other. And carbon must form 4 single bond. Distribution of the hydrogen to the number of carbon follows this strategy that every carbon, when it bonds with the other, there should be 4 bonds for every carbon. This carbon bonded with 1 carbon, so how many bonds remain to 4? 3. So there should be 3 hydrogens in the structure. This carbon in between 2 other carbon bonded with 1 and 2, so 2 hydrogen are the remainder to form 4 bonds. This carbon is in between 2 other carbon. There should be, we have to distribute 2 hydrogen on it. And then this carbon, there should be 3 hydrogen. A technique to distribute the hydrogen, always the end is in a chain form, not in a ring. The end is they take the 3 hydrogen, but those that are in between, if they do not have branches, they take the hydrogen, 2 hydrogens, and the end is 3 hydrogen, those in between 2 hydrogens, guys. Another structure, here we have got 3 carbons with the other carbon, so each carbon bonded with the 4 other 4 covalent bonds, guys. These are the 2 different structural formula, and we call, later we will learn, we call this as butane, and this is 2-methyl propane. They are isomer of each other. They are structure of isomer of each other because the shapes are different, the names are different, and the properties are different, but they have the same molecular formula, which is C4H10. But guys, sometimes it's preferred to show the structural formula in condensed form. What do we mean by in condensed form? In condensed structural formula, we just show the bonding of carbon to the other carbon, the catenation bonding. We eliminate the bonding of carbon to other elements, usually hydrogen. So if we want to write the structural formula, the condensed structural formula for this expanded structural formula, it becomes a CS3, CH, CS3, CS3. Why? As you can see, here we have got the bonding between, 3 bonding between the carbon to hydrogen, eliminated, it becomes CS3 only. And then the bonding between carbon to carbon must be represented. The bonding of this carbon with 1 hydrogen eliminated to form CH, and then the bonding of this carbon to other carbon is represented. This carbon to the other carbon is represented. This carbon's CH3, the bonding of carbon to other element, eliminated the bonding, and then we eliminated the bonding between this CH3, and this is the condensed structural formula. We prefer and we deal mainly with this condensed form in the section 3 and section 4. It's better to know how to draw the condensed structural formula. In terms of the structural formula, does it show the three-dimensional shapes of the atoms? No, it does not. Instead, we have got two models of representation. One we call as a stick ball model. The balls represents the atoms, and the sticks what? The bonding. The ball represents the atoms, and the sticks are what? Are the bonding. The ball stick model represents in this by the balls, which represent the atoms, and the stick represents what? The bonding. For example, here we have got a carbon. The green ball is carbon. We have got two green balls, and then three hydrogen. The blue balls are the three hydrogens. Here we have got three hydrogen as well, and the oxygen there represents by the red ball. And another model, space filling model. In space filling model, we do not show the sticks, we just show the balls. Space filling model. These are the carbon, and then bonded with the hydrogens, and oxygen with the hydrogen as well. So that's the space filling model, and this is the ball and stick model, guys. Let me draw some structural formula, more practices in order to write the condensed form. Let us have some of the other structural formula and then condense it. Here there should be its ending 3, 2, 1. Why? Because 1, 2, 3 bonds, the distribution of hydrogen should be 1. Here there should be 3, and then 1, and then 3, and then 3. This is the condensed structural formula, and then if we expand it, it becomes what? Carbon with 3 hydrogen, the other carbon with 2 hydrogen, this carbon with 1 hydrogen, and then with other carbon with the 3 hydrogen, and then carbon with 1 hydrogen, with a carbon 3 hydrogens, and then carbon with 3 hydrogens. These are the structural formulas, the condensed and the expanded form of the structural formula, guys. I said in the book, talked about in our book, talked about the geometric and structural isomer in the second section, but we prefer to study and talk about those two types of isomers, structural and geometric isomer, at the end of the chapter. We have to learn the naming, the nomenclature of the hydrocarbons, saturated and unsaturated, in section 3 and section 4, and then we'll be talking about geometric and structural isomer. That's the end of the session. Thank you for the attention, guys.